So, welcome you everybody for lecture 6. It is almost the last day. Tomorrow will be last day where we take care about mitigations. And today, this lecture, we move from theory and simulation to the measurement chain and the real world field scenarios that I will show you and present you. In my lecture, it will be just example of these measurement scenarios, and during tutorial, I will show you real results. Tomorrow, we will continue with mitigation, and in last tutorial, we will continue how this mitigation algorithm works in reality. So, up to now, we have already discussed how wind turbines generate complex radar clutter and how we can model it in MATLAB. So, but you know that we already also discussed that we need to make validation of our model if it's correct or not correct. And for this, we need to collect the real data measurement, because without this, we can't just make validation if it's right or not. So, today's lecture will be how collect this data outside, what we need to prepare before measurement, and so on and so on. So, first we will describe the practical challenges. Oh, sorry, I am mute. First, we will describe the practical challenges of field measurement of wind turbine echoes. So, which equipment we need, regulation, site access, what is influence of weather or non-operation states. Then I will show you design of our measurement chain. Of course, you can design own, but we just use this one that is used in measurement campaigns. That includes software-defined radios, antenna, power amplifiers, different type of filters, bandpass filters, control PC, of course some software on this control PC, storage, this hard drive or some SSD drive, and of course power generator, because we are outside, so we need also some power generator. So we first justify choices of frequency band, pulse parameters, because we are make measurement in pulse regime, and selection of waveform, of transmitted waveform for wind turbines radar measurement. I will in detail try explain in few slides what is software defined radios, because I don't know if you are like offline participants experience with these devices. And then I will, at the end of the lecture, I will summarize the key properties of the main measurement scenarios. I will show you for results. It will be locality Kámen, Skalky, Protivanov. It is in Czech Republic, and Grob Schweinbart, it is in Austria, and parameter of the radar settings. And on tutorial, we will continue with this for locations, where you will play with real measurement and this measured data. So, what is field test challenges? First, you need to have good equipment that corresponds to your parameter measurement. So, what is which kind of measurement? It will be this SDR radio. It is relatively complex equipment setup. You need relatively big car, because the equipment is not small. I talk especially about antennas. From measurement, we don't need only one, measured one scenarios, but multiple one for better validation. So it is exhausting extent of acquired data set, and of course this raw data must be later post-processed, and it is very time consuming manually work. Also, before measurement, we need to make frequency allocation and utilization, and getting license or permit processing by national authority, it could take a month. It is of course depends on individual country, but generally taking this licensing is not so easy thing. Especially if you will be in some area that is some kind of protected, like airports, close to nuclear power plant, I don't know, or some important object, if you get my point. So of course the transmission around this area or close to borders, it could be relatively tricky. Then we need, of course, make equipment placement inside that we select where we will measure. So it could happen that it's private property, so you need owner permit, airspace compliance, and so on and so on. Or you figure out that you found a really nice place and there is no access road or something. So it is not easy task. You need also, if you will go somewhere for make measurement, you won't do measurement from one place and go back. Usually you you want to plan multiple measurement around one wind turbine to get more and more data, and then it will be more complicated for you. Again, no access road and similar things. Don't forget that for running all this equipment you have electricity and you are outside, so of course there not will be accessible electricity, so you need definitely get some power generator. And the last but not least thing is weather dependency of measurement. And worst scenario that you will come and wind turbine is static object because there is no wind and you just go back. And imagine that you could get permission of transmission for 1 or 2 days. And if you are really unlucky, 2 days will be no wind and you will not make any measurement and you need to ask for another permission, and so on and so on. So, there is a first use our measurement setup methodology. We design this measurement chain first, how we say on paper. So we need to know what is required signal to noise ratio, because also you can make a measurement and then you discover that on your measured data is just noise because your reflection is under noise level and you don't see anything. So you also need to know dynamic range of your signal, because if you will be too close, the signal reflection could be so strong that will destroy relatively your SDR, or on other case you need to know if you will be in far away, then you have opposite problem, reflected signal be too low. So dynamic range, what you can expect it, is very important and you could evaluate in advance before measurement. Then next parameter important is bandwidth. We use about 40 megahertz due to some limitation of SDR, especially for data throughput. And then you need evaluate also storage rate, because if you have higher and higher bandwidth, the storage rate, like what megabits per second, will be really rapidly increasing, and then you can figure out that even SSD drive is too slow and you need just think about some different solution how to record this data. Because imagine, forget about like data recording about some USB 3.1 or something like this. It is too low, and it is not so stable. So usually this SDR works with LAN, and there is in our software defined radio is 1 gigabit Ethernet and 10 gigabit Ethernet. I recommend you from our experience 10 gigabit Ethernet. but what I can say, it is not so cheap and it is not so usual until now, 10 gigabit Ethernet. So, but it is accessible. So then you determine SDR model, and again it is based on your previous parameters that I already mentioned, antenna gains and sampling frequency. So it is like base parameter. And if you could check my figure, you can see that heart of our measurement chain is software defined radio. Then we have some control PC and storage. It is like hard drive. So of course control PC includes software that controlling this software defined radio and so on. Everything need power supply. Amplifier need little different voltage, so we just put laboratory power supply just for explanation. And then we have transmitting and receiving antenna. Maybe somebody of you can complain, okay, we still talking about radars, one antenna, monostatic solution, and now I have two antennas. Yes, it is how we call it, quasi-monostatic solution. So it is almost monostatic. And why almost? Because transmitting and receiving antenna is like 1 meter far each other. And why we use this? Because we don't need this circulator that for how to say, we don't need switching between transmission and receiving point, but just we make continuous measurement. So we are transmitting and receiving by other antenna, but it is almost like monostatic solution, but there is complete isolation between transmission part and receiving part. So we not need check all this isolation between transmitting, receiving, because we have two antennas. So for us it's like simplification. And why I call it quasi-monostatic, because transmission and receiving antenna is almost in same position, like 1 meter difference, 1.5 meter. If it will be like 100 meter, 50 meter, 1 kilometer, 10 kilometer, then we call it bistatic solution, but it is completely different story. So, okay, two antennas, but it is almost monostatic solution, just for explanation before you will start complaining. So, also you already discover that our transmitting receiving antenna, there is not any gear, so it is not rotating, right? We don't use rotation antenna, but what is difference between rotating antenna and non-rotating static antenna? If I will have rotating, that I illuminate my wind turbine only some small period of time. If I have static antenna, that I make illumination for the whole time and get just reflection. It is similar like if you have rotating antenna and always record, always select from the whole one rotation only part. When you make illumination of antenna from each rotation and put like one by one, you will get something similar. Of course, this solution of us will have one big advantage, because when you have rotating antenna and rotating, of course, wind turbine, you don't know and there will be, of course, different some rotation speed. Then you will always illuminate it only part of rotation. But with static antenna, we can see the whole rotation because we are illuminating like the whole time continuously. So you could better discover all these phenomena, all these sinusoids, all these DST component, and all these things. So for this reason, we select this solution. So there is also a big limitation on single shot measurement time that is based on mainly bandwidth and sampling time. And for our measurement we select about 40 megahertz and sampling rate I didn't remember, you will saw it later. and we can't increase more. Even SDR was able to do it due to limitation of cache size, because the install overloading of this cache and measurements stop working. So first we make measurements like dry verification, when we just interconnect all things and test in our laboratory, just without measurement of real data, but you need to validate that everything's working and be sure that on first try, second try, something will be always wrong. So you need really careful test before you go to outside. Then we make outdoor verification, including antennas. It was on closed local site without wind turbines, just for verification. By the way, on this test we was just on field where we driving just car to show it if we can see changes in Doppler of how like moving the car or something. And again, it was like 3 kilometers, 5 kilometers from university, so it is close. If we forget something, we can go back. If something wrong, we are close to laboratory. So it is like for validation that everything will be set up as we need before real measurement. And then we go to outdoor signal acquisition of wind turbine site. The first site was about 60 kilometers, second site was about 120 kilometers, and Austria it was about 350 kilometers. Believe me, you don't want just figure it out after you drive 350 kilometers that something is wrong and you need go to back without any measurement. So there is some few photos that I found it from labs at testing. This is SDR radio, so you can see just we have uncovered how looks inside. So it is one transmitter. Okay, one is transmitter and one is transmitter and receiver together. So you can use it like 2 channel transmitters or 1 transmitter and 1 receiver. So there is multiple modification how you can use this SDR. And why like this? Because it is just software defined radio. So you are switching how you need. And these blocks you can, okay, this is main board. There you have 1 gigabit, 10 gigabit, that you have RF in, RF out, and so on and so on. And this is like there is under this is FPGA, so you can even process in FPGA if you don't process signals offline in MATLAB. You can directly program FPGA and work there. And this is TXRX and TXRX. 160 is 160 megahertz bandwidth, if I remember well. So it is like classic SDR radio, so it is almost digital device because it is comes from antenna, then some amplification, filtering and AD conversion, and from AD conversion it is just digital processing. Okay, I will open. I just found some. Okay, it is not in tutorial, it is in lecture. No. Picture from our test measurement where was just car. Just check it how looks raw processed outputs. And it is individual time shot of our measurement in like range Doppler map. So you can see there is something what is not moving, static object. It not will be wind turbine, it is just taking measurement. So you can see we make some adoption, and now you can see that there just is some moving object because it is already 10 hertz of Doppler shift. So some cars start moving, just go out from our antennas. some reflection. Okay, and it is repetition, so I just want to show you. It is not any, how to say, meaningful. We need just make verification that we will be able to, that their noise is okay, that we will be able to detect moving object and so on. So it is just for testing purpose. Then we make multiple of this kind of measurement. They look little similar, but I will show you. I have 4 of them. Okay, it is similar. You can see there is reflection, movement. I think that there was even 2 cars. It was some spreading of spectra because it was close to field, and there was some agriculture devices or something, if I remember well. So basically you can see that moving objects are really detected and we can process with our measurement chain. And I will check next one. I have 4 of them. I think that this is just static. Sorry. Yes, it was, you can see static object, there is nothing else, so it was just, it was reflector, it is corner reflector for antenna, I think, just for static object. And number 4 is also just static object. I will yes, it is also just static object, so not so interesting, so I will continue. There is some few photos from measurement how looks this setup. You can see our both transmission antenna and receiving antenna. You can see that there is some stands. It must be very stable. Be careful, it is about also 20-25 kilo, because this dish is about 1.2 meters. So it is relatively heavy. It is not so easy to carry on. So you need some bigger car. There is control PC. There is some setup. There you can see power generator, of course. There is one PC. It is just second PC if we will like backup. There is laboratory. This is amplifier. And this is own SDR radios. So it looks like this, and of course lot of different connectors and like this. And this is from one side, it is from Austria, this is from second side, this is from Protivanov, if I remember well. So there was 2 turbines. But this antenna beam is relatively narrow, so you could just focus to one wind turbine antenna. Even if it's closed, if it looks like very close, so you can focus. So you can see that always you need to place somewhere. There is some small road, but you need outside of road in case of traffic or something. And own measurement, each dataset has from 6 up to 15 seconds, so you make a lot of multiple relatively short measurement, but preparation for measurement, it could take 2 or 3 hours, of course, if you don't set everything, if you just unload from car and so on and so on. So there is another pictures, but it is just from another view, so you can see how looks this measurement. So what was measurement setup? First, I need to told you that we use S-band. It is this software defined radio works in S-band, and it is highly relevant to air traffic control or military air traffic control radars. So you could use this your result with similarity to like radars, like primary radars in air traffic control, or this primary radar. So for this reason we use it. We use software-defined radio from company National Instruments. You probably all of know you. They are also big developers is LabVIEW environment, but we don't use LabVIEW. We use it only everything in GNU Radio and MATLAB. So what was there? There was also bandwidth pass. Why do you think that we use in receiving antenna bandwidth pass? Because we won't make limitation of noise in specific bandwidth where we make a record. It is just this one reason. Software on Control PC, it was based on Linux. It was Debian version, I didn't remember, but it works generally with any version of Debian. You need carefully install SDR, this National Instrument SDR, because it is, how to say, SDR, it is not typical device like you normally use in PC, plug and play. Forget that you just connect USB or LAN network and everything works. You need install special drivers, set up network connection. Usually you need two network cards, because one card for like normal communication when you need set up like download drivers and so on for communication, and second for connection with SDR. And this second one must be, I recommend you 10 gigabits per second network LAN, because you need high bandwidth. So it is based on NISDR drivers connection. It is not only one package, it is multiple package, different package, and you need to install one by one in specific order and so on and so on. So we even spent relatively long time to make like controlling of SDR from Control PC. Even this take you time, and I recommend you just prepare good manual for this. If you already have good setting, just all step that you set, just put to manual for saving your time, because after 2 months forget that you will remember again. And how was made data acquisition? We don't make record directly in MATLAB. Due to you can connect this software-defined radio directly to MATLAB, but there was some small issue about communication delay. And this communication delay caused us problem, so we directly connect to GNU Radio. Do you know GNU Radio? Yes, perfect. So it is free software. I can open link. I just edit today because I was not sure if you know it or not. GNU Radio is like software for controlling any SDR radio that is supported. I don't want to say any, but a lot of them. It is a big advantage that is free completely. It is again community development, and I consider this software one of the best controlling for SDR, and it is very easy to use. All of you know probably MATLAB, but you know that there is also Simulink. It is and Simulink, it is just boxes that you just make interconnection setting and so on. Exactly, this is GNU Radio. So it is perfect for controlling SDR. You can even make the whole signal processing by these toolboxes. And if there is not some toolbox that you need, you can easily make own through Python or different languages, and it is really relatively easy. And I like it. And best thing, it is even free, so why don't use it? And there you have web page of GNU Radio, and I want to see that there is plenty of tutorials how use it. what is this, how installing this national instrument SDR or any different, because some SDR are more simple and just need USB connection, and this is of course simplification. Maybe you know this SDR, we use it, it not has so high parameter like this national instrument, but it is Pluto SDR and from Adam Pluto, and I can say this is really nice SDR, just connection through USB. Okay, there is some picture, yes, there is picture. It has receiving, transmitting antenna, and generally you can do it so many things. And price, it is the best thing. Okay, there is block scheme. Price is about, if I am not wrong, $200, $180–200. So it is not so bad. Of course, you can't make measurement of wind turbines and reflection due to limitation of bandwidth and so on and so on. But for like working, recording a lot of signals, or just visualization of spectra without record of any services, it is really nice devices. We use it a lot of this Adam Pluto for teaching purpose, because you can see, students can see in reality how it really works. It is not only in MATLAB. So, and it is full support also of MATLAB, so you just connect and works. So I really recommend you, if you like this area, this is toy for a relatively low price, and you can play for years with this, with different implementation. And a lot of also tutorials for Adam Pluto is in GNU Radio, so even you can't program, you can just open and use it. So for GNU Radio, if you work more maybe in communication, there is a lot of like demodulation techniques. So even you can use DVB demodulation, DAB demodulation, anything, and just listen this radio or something like this. So I recommend you who like this area. This is, and GNU Radio is size is similar to mobile phone, only is like bigger size, but it is nice. I recommend you. I just figured out that I don't told you about this, and it is much cheaper. It is for normal music. Okay, we are back. After data acquisition outside, we made post-processing, all post-processing offline under MATLAB. You will make lot of how to say, data measurement, so post-processing is relatively time-consuming. I don't want to say annoying, time-consuming. And there is justification why we use S-band, because how I already say, it is relevant to air traffic control. It is in range technology limits of our SDR. Our SDR works until approximately 6 GHz. So you can see it is relatively high frequencies already. Due to S-band, the size of antenna is reasonably small, and we could use 2 antenna setup, so one dish 1.2 meter. If you will use another band, the antenna can growing up size, and it will be harder to design, and it is output measurement, so you need always transfer this antenna to measurement place, so be careful about this. Also, there is reasonable antenna beam width and contemporary illumination or reflection reception. So this antenna was, how to say, not commercially available, but it was designed just for this measurement, just for this purpose. If I remember well, price was about 2,000 or 3,000 euros, something like this, because it was custom design. We don't make developing of this antenna, we just send requirement which parameter we need, and we send to special company that make for us. And also you know that you need power amplifier, because SDR output power is very low. You don't have chance to see wind turbines at 2 kilometers, 1.5 kilometers, so on. And you know that you need really high quality amplifier with low noise number, with stable bandwidth, in required bandwidth and so on, good parameters. And power amplifier in S-band is relatively small and not so expensive. If you will go to higher frequency and higher bandwidth, the price increasing rapidly, so it is another reason, of course, why we use S-band. So, what was decision and trade-offs about our measurement design? Pulse or CV? We use just pulse operation, avoiding contemporary crosstalks, and also it is similar to primary radial pulse system, so we use pulse. You could use design with CV, continuous wave, if you are, or FMCV, it is up to you. Our choice was pulse. Signal modulation, of course, in GNU Radio we can, or our SDR, we can program any kind of pulse or pulse compression. It was just function for us, it is not so hard, but we use just unmodulated pulse. Very, very easy implementation, so why don't use it if it's not so important? Timing, pulse length or PRI, it was select based on maximum unambiguous range, you already know it. Blind range, you also already know it. And range coverage relative to blind range and power, transmission power, of course. So based on all these parameters, we make selection of pulse length, this tau, and PRI, one pulse repetition interval, or inverse PRF, it is same. Antennas has low side lobes, they have good parameters, they support all polarization, so vertical, horizontal, and vertical. So it is mean that in our antennas there was two connections, so we have like connector for vertical, horizontal, and on second vertical, horizontal. So if we will put vertical, transmission, receiving, we have vertical measurement, vertical, horizontal, or horizontal. We could make all this combination. You will see that later that selection of this polarization very influence measure data. But you probably know it very well. Wind turbine scattering is highly anisotropic and polarization dependent, what I already say. So best results was, if I remember well, in horizontal polarization and partially vertical. Cross polarization, it was, you will see, it's almost nothing visible. I will spend 2-3 slides about software-defined radio concept, where the key idea of software radio concept that many radio function which was traditionally implemented like analog in hardware or in hardware, like modulation, demodulation, mixing, filtration, it was moved to software. And for this reason, you want to make conversion to digital signal as soon as possible. And then rest is just math. It is just software defined. It is how MATLAB or something, because output will be IQ data, and then it's just samples. You could play how you want with this. So this I borrow from this link. Picture like typical block scheme of SDR. So you can see transmitter, receiver, power amplifier, low noise amplifier. Of course, you need make power amplifier because you need transmit high power, and receiving power is very low, and you need low noise amplifier to make amplification of received signal to some desired level. And why low noise? No, because you don't want to put another noise source to your received signal. Then is mixer. It is conversion to some lower frequency. And then is ADC converter or opposite DAC converter. So you can see only this is analog, this part. So only amplification and some mixer for conversion to lower frequency. And then is just converters, and from this is all, it is all just digital. And of course there is IQ data, and it is digital baseband, and there you can continue with modulator software processing what you want. It is depend on signal that you are recording. And it is completely correspond to this analog, these two parts, and the rest is just digital. It is FPGA. Again, it is just data. So, digital signal processor, DSP block in software-defined radio function. This is core of the SDR, where the most signal processing task is performed in the digital domain using software and hardware FPGAs. Who knows programming in FPGAs? Is there? Perfect. So you probably have more experience than me because we are working mainly in MATLAB, so we just use IQ data, but you could implement all this thing directly on SDR and just read outputs. It will be much better for real-time processing, but we don't need real-time processing, so we make post-processing in MATLAB. And of course, and you probably confirm me that programming FPGA is not so easy task, even with some easy functions. So for our one-time measurement setup, or if you don't program devices that will work in real time for a really long time, and it is just for some time measurement, it is not necessary, so we don't use this FPGA and just go to MATLAB. We can discuss later together. For receiver, this DSP processor perform tasks like example interpolation, decimation, digital mixing, demodulation, or other waveform analysis. For transmission, generates baseband signal, performs digital up conversion, prepares signals for transmission. All these signal processing things you could do it on FPGA generally. Then there is user interface application layer. We use GNU Radio. You can use, but also MATLAB, Python. Maybe you have some other ideas which software you can control. We use mainly this three: GNU Radio, MATLAB, Python. I don't know if you use. Okay, LabVIEW, I forgot, of course, it is National Instrument SDR, so LabVIEW is supported. Yeah.
But sir, all the software are paid.
GNU Radio is free. Python is also free. And LabVIEW Student is also free, I think. But it is just academic licensure, like for student, yeah. And MATLAB, you need to have some site license, but you have site license in IIT, like for academic, yes. But there, sorry? Yeah, and Python, okay, Octave. It is alternative of MATLAB and very similar functionality and syntax of, so yeah, Octave. If you don't have MATLAB, you could use Octave. I suppose that will works also very nicely. We have license same like you, so we use MATLAB. And any other software that you think that we can use it for this like user interface of this SDR? I don't know now. I think that we'll Scilab. Okay, I don't know it. I will check it later. Thank you.
Like MATLAB.
It is like MATLAB. I will check it. I don't know this alternative because okay, we have MATLAB the whole time, so I don't need this alternative. But thank you for recommendation. I will check during tea break this one. Okay, we use USRP 2954. There is picture of front and back. So this is front, so you can see it is this one, and from back you can see this one. So there is of course power, 1 gigabit, 10 gigabit Ethernet. Be careful, for 10 gigabit you need like special adapter for connection. Is reference output, reference input, good connection, and we testing it is this with green, how to say, button. It is PCI Express 4, high data bandwidth, but you need of course have on other side also same things. So it is not usually in standard PC. You need probably buy some conversion card or something like this. Or you need to have like hard drive disk from National Instruments. This is this parallelly connected SSD disk together. Yeah. Because we have two of them, about 60 and 80 terabits of data, so we can use it for record. Then there is triggers in out and GPS antenna. There is also, if you need exact location, you could put external GPS antenna. In front it is JTAG for programming, RF0, it is TXRX, so you can see this connect, you can use it for transmission receiving. This is just receiving, and RF1 transmission receiver again. So it is like you can use like this for receiving, so like 4 channel receiving SDR, or you can use it like 1 transmission and 3 receiving, and so on and so on. And I want to say one thing, I forget that even if you will buy this one, this part is independent. So even you can use only one UBX160 and this could be empty. So it will be just 2 channel, if you get my point. We have 4 channel, but you can have it like 2 channel. And if something wrong happen with this part, we will just replace this part. But you don't want, of course. This is USRP block diagram. Okay, I will start there. Control PC. 1 gigabit, 10 gigabit connection or PCI Express. Clear, I think. This is some packet routing, and this part is for transmission, and this part is for receiving only. Or this one, not this one, and for transmission and receiving, of course, because you can switch. So there is DAC conversion, low pass filter at 80 megahertz. This is just conversion of phase. This is direct path from 500 megahertz to 6 gigahertz radio path, transmission amplifier, and go to antenna. Or you can go this way from bandwidth 10 megahertz to 500 megahertz. There is filtration, phase loop lock, and so on and so on, and go to RX2. So generally there is 2 paths, because you can't have it one path from 10 megahertz up to 6 gigahertz. So they have 2 way, like for one bandwidth and second bandwidth. And this is really similar to the first one, only there is 2 receiving parts. So you have low noise amplifier, filtration, direct path, and low bandwidth path, if I can say, drive amplifier, ADC conversion, so there is digital data, receive control, and you gathering data. And of course, this is just valid for USRP. I have block scheme from National Instrument documentation, but generally, a lot of them looks very similar. Different parameters, different filters, and so on, some small differences, but the general point of view will be same. There is some parameters that I will select. I will highlight only some of them. Okay, frequency range from 10 MHz to 6 GHz. It is very impressive. It is very, very high range, and for this, even this price is little increasing, of course. This Adam Pluto that I mentioned, this blue one, small one, it is up to 3 GHz. Okay, officially it's up to 1.7. No, it is. It can be software unlocked to higher frequency where it's not officially supported, but works. How to say? Of course, in your responsibility. It was not advice. Okay, instantaneous real-time bandwidth that can process is 160 MHz. Enough. It is impressive. It is really nice parameter. Maximal IQ sample rate is 200 megasamples per second for transmission and receiving. It is really nice also. Converters, ADC converter is 14 bits and DAC 16 bits. So for small box, nice parameters. The output power is between 17 to 20 dBm, or it is for different bandwidths. You can see RX gain from 0 to 37 dB, maximal input power minus 15 dBm, noise figure of 57 dB, and memory 1 gigabit, and I think that is all. There is some, of course, list of FPGA parameters, but I don't put it because you can read easily manual. It is freely available. So now I have one small question to you. Antenna, you will be probably agree with me, that is type of filter. In which domain work antenna? Time domain, I didn't agree completely.
Spatial domain.
Space domain. You missing two more domains. Frequency domain, of course. And we already talked about it. Polarization. Exactly, yeah. Sorry, you know it. And polarization domain. Exactly. So, space, it is narrow beam, isolating single turbine, wide beam, and so on. So, it is space domain. Frequency, of course, frequency selectivity. You have designed for specific frequency name. So, this was in close to our desired frequency band. And polarization is clear, vertical, horizontal, cross polarization. Perfect. So, I will give you few words about transmitting and receiving antenna. We use two of them due to simplification of isolation to avoid needed a high power circulator. It is better for us. So it is quasi-monostatic, I already told you. Their company parabolic antenna was JRMC 1200, 2.9, MIMO, multiple input, multiple output, and this is frequency. And 1200, it is mean perimeter of antenna. So you can see how looks like this antenna. Of course, you need two of them, or you need this circulator. And both antennas are same. It is look like transmitting antenna and receiving, but they are same. It is just pair. There you have some parameters from 2.7 to 3.1 gigahertz, gain 28 dB plus minus 1 dB, minus 3 dB beam width, 6.3 degree, pore-to-pore isolation more than 30 dB, both polarization, it was important for us, and for operating wind load, survival wind load, okay, and antenna weight 42 kilos. There you can see E-plane and H-plane of both antenna, so you can see main lobe and side lobe. How was designed this specific antenna? Sorry. I don't know if you are familiar with, and on axis Y is antenna gain, of course. I don't know if you are familiar with E-plane and H-plane. E-plane is that contains the electric field vector and the main beam, and H-plane contains magnetic field vector. So it is like E-plane elevation pattern, H-plane azimuth pattern. It is like this thing. It is for vertically polarized antenna, and for horizontal it is vice versa, opposite. Then we need power amplifier. Our selection was amplifier from mini circuit ZHL 16 watts and some numbers. You can see the wall amplifier is this one. It is very easy to use, you just connecting, so there is no issue. Range, it has about 10 watts, and it is enough for range coverage. And of course this power amplifier includes our S-band, so it was suitable. Size like this one, like this will be 15 centimeters by 15, and this maybe 30 centimeters, something like this. It is not so huge. You can also mount in and so on. Of course this is amplifier, this is some cooler, and so on. So, and it works from 1.8 to 4 gigahertz, and we need 3 gigahertz, perfect match. There is more multiple option, of course. You could select what do you want. There is typical parameters. I don't think that I need to read it. I just want to put it for you if you are interested. There is signal amplifier characteristic. So it is from datasheet. It is gain, directivity, output power, noise figure in different frequencies, and it is all. Then, if you remember well, there was bandpass filter, and we use this again from mini circuit. It is just small bandpass filter interconnect between this. It is like this one. It is really small thing. Center frequency was 2.9 megahertz. Passband from 2.7 to 3.1, exactly match to our price. Very low. It is just few euros. It was not expensive. And connector SMA, we usually use SMA connections. There is attenuation of bandpass filter, so you can see exactly in our range there is no attenuation, rest is attenuated. So it is again from datasheet. Additional equipment, we use standard PC, big one, and then we have rugged PC with military specification, because it is, if will start rainy or something, this PC still survive. How to say? And recording device was external hard drive SSD, about 10 terabytes of data. I will not read any data because it is standard laptop, but just in a rugged solution. We have 2 of them for processing, for output measurement mainly. And very important, power supply, power generator. There is not important parameters, it is standards. Oh, and you need, of course, petrol. You can't to forget. And it is all what you need, and a lot of time. So, what? How looks our time?
Yeah, means time.
Time 40. Okay. So, what do you think if we will make time 40 for 15 minutes or half an hour?
You can.
15 minutes enough? So 15 minutes. Okay. So thank you very much for attention, and we will go for tea. And we have, I think that now today we are on time. We are in half for presentation after